coordinate system. I have the first axis, second axis, not E, second axis, and the third axis here. If I have a vector in this system, vector, let's see, it's R. If I project it to the 1 and 2 plane, and then the rest up to on the first axis, then this distance will be R1. If I do this the same up to here, this distance will be R2, and the value that I have over this axis will be R3. So this means that the vector R, you can write it like this: R1, R2, and R3, or R1, E1 plus R2, E2 plus R3, E3. So what is this E? E is unit vector along each axis. So I can write the vector R in this form. I can write R is I from 1 to, is 2 is for this, to 3, R, I, E, I. So it means that I have expanded the vector R in terms of unit vectors. These unit vectors are bases, are for base functions. They will show how much the direction of this, how large is the contribution of this vector along each axis. From, for example, R1 here is the contribution of R along the first axis, contribution of R vector along second axis, and contribution of R along the 3 axis. So if I have, for example, infinite number of base functions, then I can write simply like that: Ri, Ei. Now let me compare this equation with this expansion with the spherical harmonic expansion. So I have gravity, the potential, and summation R over R, m plus 1, m minus n at n, v n m, y n m, theta r1. Now look at this vector that I wrote. I from n to infinity, R I E I. So if you remember, that's the damping factor. It shows that it's based on the distance from the surface of the Earth, shows how much frequency are damped or are reduced. And the rest here is a scale factor. This EI is equivalent to this one, and RI is equivalent to VNM. This is in fact VNM. VNM is in fact contribution of the gravity field with this base function, similar to what we have had for this vector expansion. This is, it said how large the function is along this axis or along this base function. And here it says how large the potential is for this spherical harmonic with this frequency. It's similar to Fourier transform. Fourier is also simple. Fourier say that if we have a signal like this signal is, for example, a frequency, a signal like this, plus some small frequency plus smaller frequency, and it means that you will try to model this signal by sine or by sine or cosine functions. This frequency by sine or cosine functions, and this is a large function with long periodic function, and you will do it with the small periodic functions, and you will try to obtain it by harmonics. So now orthogonality. Orthogonality. Let me explain it like this. Again, I have a system of a coordinate system 1, 2, and 3, and I have a base function e1 here, e2, and e3. So what is orthogonality? It means that if I multiply the vector ei to e2, it will be 0. The inner product of this vector is because they are orthogonal. E1 to E3 is 0. E2 to E3 is 0. And E1 by E1 is 1. E2 multiplied 1. And E3 multiplied by E3 is 1. So you see that if you multiply this base function by itself, it's a unit vector. For example, E1. If I write it like that, let me write E1 to more clear form for you. E1 is 0, 1, 0, 0, and E2 is 1, 0, 1, 0. So if I multiply E1 by E1, it will be 1. It's clear. E2 by E2 is will be 1. E3 by E3 is 1. But if I multiply E1 by E2, it will be 0, because 0 is multiplied by 0, 1 multiplied by 0, 0 multiplied by 1. So this property is called orthogonality. But what about spherical harmonics? So of course we cannot like it like a simple inner product like that, but we can write it this inner product in integral form for spherical harmonics. What does that mean? Let me explain it. So as you saw, I multiplied two base functions. For example, E1 till E1, E. So I will write for E1, Y and M, theta and lambda. I multiply this Y n prime or M prime, theta and lambda. So I want to multiply, but this is a spherical function. This is not simply that I can say that it is 0. I should have an integral behind it. Say the integral over whole sphere. This is a surface integral with respect to the surface integration element. I will write it as 4 pi delta n prime. I continue the rest here, n m prime. So what does that mean? It means that in the case that n is equal to n and m is equal to m prime, this will be 4p. This will be 4p, 4 pi. Or if n, or if they are not equal, n prime, it will be 0. This is exactly what we saw for the base functions for E1, E2, E2. When they are multiplied by themselves, they are 1. When they are multiplied by the other one, the other base function, because of the orthogonality property, they are 0. This is exactly the same here. In some lecture, some places, you may see that they write this 4 pi here. They write 1 over 4 pi. Then in that case, they don't write this pi. It will be more similar to the base functions for the vectors I explained, E1 and E2. It will be 0 or either 0 or 1, depending on this base function and the frequencies. So spherical harmonics are orthogonal. So that is interesting because when they are orthogonal, we can do many things with them. What? Let me explain analysis. Spherical harmonic analysis. Let me start first with the example of the vector that we already have. I have a vector. I have expressed this vector based on the base functions, and these are the contributions along each base functions. And I want to determine this coefficient, this contribution with Ri. So how do we do that? For example, let me expand this completely. I write it R1 E1 plus R2 E2 plus R3 E3. So now I want to determine, for example, Ri. I will write the first one. I will multiply both sides by E1. E1 multiplied by I dot will be R1 multiplied by E1 plus RE1 multiplied by R2 E3 E1 plus E1 multiplied by R3 E3. So we have already discussed that multiplication of these are E1 and E3 is 0. E1 and E2 is 2. Is also 0. The only one is not 0 is that one, which is 1. Therefore, if I multiply E1, EI by the vector, then I got Ri. Or I can write it in more general form. I said, okay, Ri multiplied by EI will be Ri. It is the same. So it means that if I multiply this EI by this summation, Ri EI, this will be like that. So how is the situation with the spherical harmonics? Let me clean this one. So think that R special cases for the terrestrial data, R is equal R. Then the potential at point R, then will be R, will be summation and 0 to infinity m minus n v n m y n m theta and lambda. And my goal is to determine v and m. How do we do that? Let me write this short v instead. V is, or v theta lambda, equals to, I multiply this by y and m, theta prime, theta prime lambda prime, another function, and will be n is equal to 0, m minus n to n, v and m remains here, and I will multiply by n, m prime, theta prime, m prime, and I will continue this here, and I am theta lambda. So I did exactly the same thing that I did for the vector. I multiplied the base function to both sides. Now I take the summation from both sides of this equation. What does it mean? It means that I will write summation is the integral over v theta prime lambda prime y and m theta prime lambda prime d sigma equals sigma n sigma m minus n m v and m, and I don't have it, not have a space. I go down there, continue here, and so it will be integral y n prime theta prime lambda prime multiply 1 and m prime theta lambda. I will continue. The sigma. So, do you know this? This is orthogonality, based on the orthogonality property of the spherical harmonics. This will be 4 pi delta n m prime delta m m prime. What does that mean? This means that if I put it here, I will get, let me write it down, v theta prime lambda prime y and m prime theta prime lambda prime d sigma is, if I put it here, this term, if I put here 4 pi Kroneker's delta here, if I put them here, this all frequencies which n and for all n and which are not equal, all terms will be 0 except the cases that n is equal m prime and m is equal to m prime. Therefore, these both summations will vanish. Then I can simply write v n prime m prime 4 pi. So we are almost there. So v and m will be 1 over 4 pi. This 4 pi goes here. Integral of the v function theta prime lambda prime y and m. I can clear this part. Theta prime lambda prime and yes, that's spherical harmonic analysis. So it means that if you have if you have the potential at the surface of a sphere is full sphere, unit sphere, then you can compute the contribution of this potential for this base function, for this frequency, by this integral formula. So these gravity field models that you will see, and they are available, they computed from satellite data, they are all based on this principle. So they have the potential they measure the potential or some functionals of potential that I will explain later. Some functionals of potential. Then by this spherical harmonics and the orthogonality property, they will determine the spherical harmonic coefficients or the contribution of the potential along each spherical harmonic function. Okay, that's analysis. Spherical harmonics analysis. It means that we have the function V over a sphere, and based on this frequency, and we compute the spherical harmonics and compute the spherical harmonic coefficient or contribution of the gravitational potential at the base function with the base function. If we use the potential to get the spherical harmonic, it's called analysis. And if we have the spherical harmonics, spherical harmonic coefficients. Let me see, write it like this: m minus n to n minus theta prime lambda prime. This called is synthesis. So from the spherical harmonic coefficients to the function, and from the function to a spherical harmonic coefficient. So this type of solution is of the spherical harmonic or synthesis is called also a spectral solution. Spectral solution. Spectral, what does it mean, spectral? These contributions, actually contributions of the function along its base function, is called actually a spectrum. And when you write spectral, it means that you are presenting a function based on the spectral or a spectra of the function or the spherical harmonic function.